Well, last time we just made a very brief introduction to analytic treatment of three positions of a moving plane. If you remember, the graphical treatment, especially if you're after a four bar, is quite simple. Just let's remember it. If we have three positions of a homologous point, it defines a circle uniquely. So once you select, say, A1, A2 and A3 are known based on the positions of the plane. So using any CAD software or GeoGebra or something similar, I'm not forcing you to use a specific software. You can use anything you feel is suitable for you. If you're good at NX, use it. Or if you're good at SolidWorks or CATIA or whatsoever, use it. If you know these 3 points, then the center A0 is fixed and it's unique. Am I right? Because these 3 points define the circle uniquely. And you can select another point, say B, then its 3 positions are fixed. It defines another circle uniquely whose center, which we call B0, is fixed. So you can construct the four bar. Very straightforward. However, we should be very careful because although the mechanism exists in these 3 positions, the four bar linkage, 1 or 2 positions may be at the other branch. So it may not move from 1 to 2 and 3, or from 1 to 2 it may move, but it may not move to 3, which is the first thing we have to check by the analysis. And we have the tools to do that from homework number 0. The other thing, the link lengths may not be suitable. One link may be too long, the other one may be too short, etc. Or the locations of A0 and B0 may not be suitable if it's a specific design. But by changing or by how you select these points, still you have 2 free parameters to select this, say it's X and Y, 2 free parameters to select this, it's X and Y. You can change the four bar, okay? So we have many alternative four bars to overcome the design constraints. This is one way. Now, for certain problems, you may like to select the fixed pivots A0 and B0 at certain locations because maybe the design constraints on the fixed pivots, or sometimes we call them the center points, might be stricter than these. And what can be done is very simple. We utilize the kinematic inversion. That is, we fix the moving plane. We let the fixed plane to move. Then what happens is we will have the rotations inverted. The poles will become pole triangle. That's not very important for brute force design. And the what we call circle point and the fixed pivot center point change the roles. So you have 3 homologous center points in the inverted motion, which define the circle uniquely. So you can select them as you like. And the circle points will be centers of the circles of the inverted motion. So they will be defined uniquely, okay? So that's another way to do the graphical design. Of course, we had seen the pole triangle, image pole triangle, the ground points, etc., the limitation on the shortest crank length, etc., which are certain, if you like, details, if you would like to do a more detailed design. Today we will discuss the analytic treatment, which was based on Erdmann and Sandor's analytic method, which was based on two unknown vectors. That is, we would like to determine such a 4-bar, but it's not defined yet, okay? We don't know it. What we know is only the positions of the moving plane, which are in analytic treatment designated by a point and the angular positions of the plane. So P is a representative point in the plane, which we can say is, it can be the origin of our coordinate system. Remember, this lowercase xy is arbitrary. So you may select P1 as the origin of your coordinate system in position 1, P2 at 2. So these O's or P's are again homologous points, but rather than using two homologous points, we select one point and one angular orientation. That's again arbitrary, okay? You just pick a plane like this, okay? Say this is your plane. If you like, you can use this side of the paper as your reference, but if you like, you can draw a line like this, and you determine how much it rotates in between the positions, plus how much your representative point, which you mark on this plane, displaces, okay? So the graphical and analytical treatments use different approaches. In graphical treatment, you had 2 points defining this plane, and you have its homologous positions, okay? Whereas in analytic treatment, we define the positions by the displacement of the representative point and the relative rotation between the two. For example, in this, actually the plane rotates in clockwise direction, okay? It's moving like this, and this is alpha j. It is the difference between, say, this angle. Let me just draw it. It's better, I guess. And let's see. So say this is my phi 1, and this is my phi j for jth position. So phi j minus phi 1 for our case is negative because phi j is smaller than phi 1. So the plane is rotating clockwise, and alpha j is that angle whose magnitude for this specific case is negative. And we are actually trying to find a 4-bar linkage. We would like to select A and B and corresponding A0 and B0 for this mechanism. So our vectors WA, which is from A0 to A, and the other vector, which is ZA, which is on the moving plane that connects A to the representative point, are unknowns. We would like to determine them, okay? And we represent them by complex numbers rather than Cartesian vectors, I, J's. It's much simpler, okay? So what we have is WA plus ZA, which are two unknowns, is our representative point in position 1. And when it displaces by an amount delta J to the jth position, we reach to the position of this point in jth position, which we call PJ. So we are at here. So right-hand side of this equation tells us the location of point in the jth position. And I'm just using J for the general formulation. If it's two positions like this one, J is 2. Okay? So we are here. We travel to the same point when the mechanism moves to the jth position. So what happens is this crank rotates by an amount beta J, which might be an unknown or which might be something specified depending on the design problem we have, but it's going to rotate by an amount beta J. So WA in the rotated position, I'm sorry, I can't name it this way in GeoGebra, that's why I call it WA rotated, but it becomes WA e to the I beta J because I'm rotating it by an amount beta J. So this is what I have. So this is actually point A in the jth position, AJ. And then I have this vector, which is, since it's on the moving plane, rotates by an amount alpha j. So I have ZA e to the I alpha j, and I come to the same point, which is PJ. So this is how we derive Erdmann and Sandor's, sometimes called the dyad equation. Actually, it's not exactly this. We just manipulate it slightly, but this is how it's derived. Any questions? Actually, we discussed this last week as well. I guess it's clear. So what we do is we have the same WA on both sides. So we take this to this side, we take this to that side. So we obtain from this equation that equation, and actually we also omit sub A's, and actually it's true for sub B's as well. Just let's see. You may have this WB plus ZB plus delta J is equal to WA e to the I. This time, this rotation, we will call it beta prime, which is not the same. But this ZB rotates the same amount, alpha j, okay? So this is going to be B prime, but this is going to be the same because these two vectors are on the same rigid plane. So we can also write it as B, 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 and the crank rotation will be different, okay? So WA and WB will be different, ZA, ZB will be different, beta J and beta J prime will be different, but alpha J, it will be the same. It's the rotation of this plane, it's unique, will be the same. So you could write it for A, B, or any point you like. So actually, this is the general form of so-called dyad equation. Be careful, this dyad is not tensor, it is just two vectors added. And if you can solve this equation for various problems, you can design the 4-bar analytically. So that's the general form, and we will discuss how it is solved for different design problems. Before that, let's discuss some of the terms. Actually, delta J is the displacement of point P in position J, and you can also determine it from its position vectors. This is the position vector in plane position 1, and this is when it's in position J, if you like. And alpha J is the rotation of the moving plane from position 1 to position J, which is actually the difference between the angular positions of J and 1. And beta j is the corresponding rotation of the crank when the plane moves from position 1 to position j. So, actually, if you like, this is another figure where this green vector is R1. It is the position vector of point P in position 1. And this is dotted Rj is the position vector of point P in position J. So it shows those. Also, I have alpha 1 and no, these should be phi. I'm sorry, it's what does it? Alpha, they should be phi. This is phi 1. Let me correct it. Actually, we had it in the previous figure, but this is, let me take a note and correct it in the slides at least. This is phi 1, this is phi j, and the difference is actually alpha j, which this time is clockwise, and actually this is where we have the instant center, it intersects it. So this is the general form. And we will see how we can solve this or modify this equation based on different problems. The simplest problem is we have the three positions of a moving plane defined by the position vector of the representative point 1 and the angular orientation of the plane 1, R2, phi 2, and R3, phi 3. That is actually you define, if you like, the origin of the position vector of the origin of the moving plane in positions 1, 2, 3, and the angle between x-axis of the moving coordinate system and the fixed x-axis 1, 2, 3. Well, we can determine delta 2 and delta 3 very easily. Delta 2 is R2 minus R1, and delta 3 is R3 minus R1. So we know these, and alpha 2 is phi 2 minus phi 1. Alpha 3 is phi 3 minus phi 1. So these two are known as well. We have to be a little careful, okay? This is not like 301. We have two complex equations, which stands for, if you like, four scalar or real equations. And some of our unknowns are complex, which are W and Z, okay? In 301, all of our unknowns were real. We were splitting the equations into real and imaginary parts. But here, W and Z represent plane vectors. Therefore, they are complex numbers. So we have two unknowns for W, the real and imaginary part. We have two unknowns for Z, the real and imaginary part. But beta 2 is a real angle. Okay. So we have one unknown for this, one unknown for that. So what happens is this. We have two complex, four scalar equations in 6 scalar unknowns. W and Z are complex, so we don't know their real and imaginary parts. And beta 2 and beta 3 are real angles, which we can say are scalar. So we have actually 6, if you like, scalar or real unknowns. Now, the good thing is dyad equations are linear in terms of these two complex unknowns, but nonlinear in beta 2 and beta 3, the angles. What we do is for 3 position synthesis, since we need to determine W and Z, which actually define the locations of A and A0, I'm going to discuss this in a minute. And beta 2 and beta 3 are crank rotations. If it's just a bare 3-position synthesis, if we have 4 equations but 6 unknowns, that means we have 2 free parameters. We can select the rotation of the cranks arbitrarily as we like. Say it can rotate 30 degrees from position 1 to 2, and it can rotate, I don't know, 75 degrees from position 1 to 3, which might be a trial. Okay, so we can select these, then we can solve for W and Z very easily. Am I right? Because the equations are linear. So that's a good trick. So select a set of beta 2, beta 3, obtain, say, a unique A and A0. Select another set of beta 2, beta 3, say beta 2 prime, beta 3 prime, obtain B and B0. Form the 4-bar, analyze it. If you're lucky, it would run. Mostly we're not that lucky. So you need to change these, try others, and after some iterations, you're going to find a suitable 4-bar, okay? So what happens is, starting from the position of your representative point P1, negative Z vector locates your circle point A1 in the position 1. And then from A1, a negative W locates your center point A0, okay? When you try another beta 2, beta 3, the negative Z is going to show you B1, and from that point, negative W shows you B0. So you can obtain, by changing beta 2 and beta 3, different 4-bars, and then try them if they're running, if all 3 positions are in the same branch, etc. There is no shortcut for those. But this is how we perform the analytic 3-position synthesis straight ahead, okay? And this time, unlike selecting A and B and finding a unique A0, B0, our free parameters are the rotations of the cranks for the 2 cranks. So you will have 2 free parameters for one of the cranks, say A0, let's say. You would like to find for this mechanism for the 3 positions. So one set of free parameters is beta 2, rotation from position 1 to 2. The other is beta 3, which is from 1 to 3 for this crank. The other one is the rotation of this crank, beta 2 prime and beta 3 prime. So you have 4 free parameters. It's the same, but the parameters are different, okay? It's not you go on the plane and change the location of A, but it's the set of beta 2, 3 and beta 2 prime, beta 3 prime. So this is what we do, okay? So it's just, if you like, the same picture, but you look to it through a different perspective and you obtain different free parameters, but the number of free parameters, it's the same. It's 4 in total, if you would like to design a 4-bar. This can be programmed and you can run the program very easily. However, unlike the graphical one, you won't be able to see it until you get the mechanism and analyze it, okay? So the graphical problem, it's more visual. You can see what's going on while you construct the mechanism, so you can maybe make educated guesses in selecting the locations of A and B. Here you don't have it, but you can just write a code that would run, that might generate you sets of or plenty of A's and B's, and then you can just select from that set certain values and then analyze the mechanism and see what's going on. So none is superior to the other. Each method has its own advantages and disadvantages. So that's the major, I would say, derivation. Now, what is interesting is the link lengths of the mechanism are like this. A2 is the magnitude of the complex number WA, okay? It's real part of WA square plus the imaginary part of WA square and the square roots summed. Link length A4 is WB. So these are the lengths of the two cranks, okay? Which are these lengths, okay? This is A2, this is A4, and this is A3, which is the difference of two Z vectors, magnitude. And the fixed link length, which is this one, is actually WA plus ZA minus WB minus ZB. This is in parentheses in magnitude. Actually, you may have another minus sign here as well, but since it's the magnitude, whether it's minus or plus doesn't matter. That's why I simplified it. But, so this is actually what we are looking for in terms of 301. But actually, those complex numbers contain more information than just the simple link lengths, okay? If you're after the link lengths, okay, these are the link lengths. But you can represent those links as vectors as well, because initially you don't know the location of A0, so you don't place the origin of your coordinate system to A0 or maybe B0, but A0 is at an arbitrary location. So that's why actually these complex numbers which represent the vectors contain more information than just those link lengths. And let's see that. Actually, A0, A1 vector is WA, B0, B1 vector is WB, A1, B1 vector is, we may call WAB is ZA minus ZB, and A0, B0 vector, we may represent it by a complex number like this, WA0, B0, is this. So now we can place our 4-bar on an arbitrary coordinate system or complex plane where A0 is not at the origin. And we can also determine the initial crank angles, which are arguments of those complex numbers, okay? Because WA and WB are actually the two vectors that are from A0 to A and B0 to B. So that information is going to yield an alternative kinematic analysis, which we will discuss after our 10 minutes break. I'm not 10 minutes, I'm sorry. I'm still living in the good old days. We will have a short 5 minutes break. After that, I will show you how it can be utilized. Continue. So actually, this extended information leads to an alternative kinematic analysis, which is like this, okay? The mechanism is in this initial position. These are complex numbers showing the positions of the links, and actually this is a fixed vector. These are the two cranks, and this is the coupler, or this is link 2, this is link 3, this is link 1, this is link 4. So rather than A2 e to the I theta 1, 2, which is a complex number, we represent it by WA, okay? That we have obtained from the design. So it's up to you, actually. You don't need to use this, but that's an alternative kinematic analysis where this is equivalent to A2 e to the I theta 1, 2 in the first position. This is A3 e to the I theta 1, 3 in the first position. This is A1. This is A4 e to the I theta 1, 4. So what happens is when you rotate one crank by theta j, actually this is theta 1, 2 in the jth position. This is theta 1, 4 in the jth position. And this is theta 1, 3 in the jth position. So you obtain something like this. But can you see? This is actually what we know. When the plane moves from position 1 to position j, it rotates by alpha j. So this is something specified by the motion. And actually, theta j and psi j that we represent are actually, this is the beta j that we specify to obtain the position, and this is beta j prime that we specify to solve the dyad equations. So these are the rotations that we specify. So actually we can rearrange the equation like this, okay? So that we can solve for these two, okay? I would like to eliminate alpha j's. And again, I will just follow a different procedure than we were using in 301. That's an alternative procedure. So I have a complex equation. I won't split it into its real and imaginary parts and then try to eliminate this alpha j, but I'll just write its complex conjugate. So these over bars are complex conjugate of this number, and we know that complex conjugate of e to the I something is e to the negative I something, okay? So this is my complex equation. This is its complex conjugate, which, if you like, is the mirror image of this with respect to real axis. And rather than squaring and adding real and imaginary parts, I can multiply the equation and its complex conjugate by itself, so that this, which stands for theta 1, 3, is going to be eliminated, and I'll obtain a relation between theta 1, 2 and theta 1, 4, like we did in 301, okay? So that's another, as I said, alternative procedure. You don't need to use it if you feel comfortable with our good old 301 analysis, no trouble, okay? This is just, I would say, an alternative method in complex numbers. So when you multiply these two, this will be eliminated. I'll have WAB conjugate is equal to, then I multiply this with this one, which I obtain all of this. And if you just watch what is going on, those yellow ones, so I just tried to group the terms somehow. The yellow ones are all a complex number multiplied with its conjugate, okay? So yellows are complex number multiplied with its conjugate. Now, these orange ones are actually, you have WA0B0, WB e to the minus psi j, and this is completely complex conjugate of this. WB bar, e to the I psi j minus e to the I psi j, W bar A0 B0, WA0 B0. So this and that are complex conjugate of each other in addition, okay? These two. Similarly, if you check the green ones, where is the other green? I don't see it, boy. That's a mistake, the term is missing. I have the same equation retyped. I don't know what happened to that. Let me just take a note on this. Actually, the same equation should be copied here. Maybe it just didn't fit into, but, well, these are the two terms which should be there. So it's WA0B0, W bar A0 B0, W bar A, WA, e to the minus I theta j, e to the I theta j. So everything is complex conjugate of each other, okay? And then this blue-purple term, which is actually slightly arranged from the equation, WB, WB bar, WA bar, WA, e to the negative I psi j minus theta j, e to the I psi j minus theta j. So I have, other than those yellows, complex conjugate things added with each other, okay? And if I just rearrange this equation, what I have is this. You see, these are just things in addition, but they're complex conjugates of each other, and I can write these two like this, those two like this, and those two like this. And this equation looks like a complex equation. That's a complex number, that's its conjugate, or this is a complex number, this is its conjugate, we multiply it with complex numbers. It looks like this, but no. It turns out to be a real equation. Let me show you why it is real, okay? It's not complex, it's real. Number one, if you multiply a number with its complex conjugate, this is what's going to happen. A plus IB, whatever A is, whatever B is, they are real numbers. Its complex conjugate is A minus IB. So if you multiply the two, it becomes A squared plus B squared without the imaginary part. Okay? So all of those yellow things are real. Number two, if you add a number with its complex conjugate, like those, the colored groups, A plus IB plus A minus IB becomes 2A. That's also real, the imaginary part drops. Okay? And actually, this has an extension. If you apply it to Euler's identity, this is e to the I theta. This is its complex conjugate. So you have cosine theta plus I sine theta for this. And for this one, it's cosine theta minus I sine theta, which is just 2 cosine theta. So that's also real. Okay? Which are for those parentheses. Okay? That's why, although this equation looks complex, it's real. It's not actually complex. So what happens is you can perform a position analysis using this equation, which yields actually the same equation that we have solved for the 4-bar, either by half tangent substitution or by phase angle method, okay? It will be in terms of cosine of psi and sine of psi for a given theta. Or if you like, this is theta 1, 2, this is theta 1, 4, just a different notation, okay? Which would yield the two closures that we keep discussing in 301, okay? So that's just an alternative method if you like. If you don't, our good old method is still there. You can use it. This is just another way of doing the same thing. Okay? So we had seen one way of using the dyad equation, which was the very straightforward use of it. We will see other uses as well. We will modify it, but can we utilize it for two-position synthesis? The answer is yes. You will have just one equation like this. Delta is the displacement of the point from position 1 to 2. Alpha 2 is the rotation of the plane from 1 to 2. We don't know how much the crank is going to rotate. We don't know the vector W. We don't know the vector Z. So we have one complex, or if you like, two scalar equations in 5 scalar unknowns. W is complex, 2 unknowns, real and imaginary parts. Z is complex, 2 more, 4. And beta is 5. So we can do something different than 3-position synthesis. We may arbitrarily select Z, which corresponds to actually selecting the circle point, that is location of A in the graphical synthesis we did. So it gives the location of the moving pivot, which is negative Z from P1. And we can also select how much crank rotation we want. Then W, the complex number, has a simple solution like this. And it's going to give you a unique W vector, but remember, you have selected 2 free parameters for that and 1 free parameter for the crank rotation. So still 3 free parameters. Just remember the graphical 2-position analysis. We were selecting A arbitrarily on the plane, and A0 would be on the line. So 2 free parameters to select the location of A, 1 free parameter to select the location of A0. We had 3 free parameters. Same is true here. Z actually specifies the location of A, but this time we don't select A0 on a straight line. We select the crank rotation, say it's 30 degrees, 45 degrees, whatever you like. So by changing Z and also beta 2, this is a real number, remember, we can obtain different cranks. Now, there is one hint. If you select beta 2, a smaller angle, you would obtain a larger A2. Or if you select beta 2 as a larger angle, the crank length would be smaller. Just think the graphical analysis. You had A1, A2, and the perpendicular bisector. Let me just sketch it here. Say this is your A1, this is your A2. You drove your perpendicular bisector. Just omit this stupid snap line. That's A1, 2. Now, if you select your A0, say somewhere here, then your crank length would be small and your beta 2, if you like, would be large. But if you select your A0, say here, that was my A0. You see, you would have, I'm sorry, I can't draw lines with the tablet, and it keeps snapping again. You see your beta 2 would be smaller. So you have the same property in graphical analysis, okay? But this time you select where your A0 is going to be. You would obtain beta 2 as a result. In this equation, what you do is you select your beta 2 and you obtain A2. Actually here, what you do is you select your A2 if you like, okay? So the same consequence occurs there. So actually it's the same image, just a different perspective. And you can obtain the location of your A0 by negative Z, negative W vector, okay, from point P. So these are actually two, I would say, brute force or direct uses of the dyad equation. But we can use it for different purposes as well. So we had seen it how to use in 3-position synthesis. We can also utilize it for 2-position synthesis, that is 2 positions of a plane or 3 positions of a plane. But there are other uses as well. And let's see them. And also we would modify the equation for different things as well. So I will continue with the other uses of it. So this was actually one of the three design methods, which was positions of a plane or coupler displacement. Now, there are others. For example, we can try path generation. That is, we may want our point P to trace a certain path. And also, we may force so-called prescribed timing. Now, this prescribed timing is a little tricky word. Actually, what is done is, timing means this crank rotates certain amount, and this point is going to move to a certain location. Now, you may say, where is the time? It's just crank rotation. Mostly in machines, the crank rotates at a constant speed. So it's going to trace certain angle in a time, okay? So it's indirectly related with time, but for steady state operation of the machines, the crank is rotating at a constant speed. So crank rotation or correlation of this point with the crank rotation turns out to be timing, okay? If this is rotating with constant speed, it's going to move from this point to that point at a certain time, then that point at a certain time. And actually, this is called a coupler point curve. And you would like to trace this point, this curve. Of course, we know that we can't design a mechanism that would trace this curve exactly, because there are infinitely many points on this curve. However, to design this 4-bar, we know we have a finite number of design parameters. It's not a CAM, okay? For a CAM, at least theoretically, you can generate any curve you like. But with a linkage mechanism, since the design positions are limited, you can only trace the curve approximately, or at certain positions, you can exactly satisfy the curve. In the middle, it's going to deviate. And actually, this figure is taken from a publication where they are doing optimization to minimize the difference between the actual points generated and the curve, which is not in our scope, but it explains what we are doing very nicely. That's why I wanted to use it rather than generating something using GeoGebra. So what we have is actually, we are given the crank rotations. So at certain rotations, we want certain displacements of the point, and we just do it for 3 points, not many like in here. But we don't care how this plane is moving. So our parameters change. Rather than given alpha 2, alpha 3, which defines the positions of the plane, it's arbitrary. I don't care what it does, but what I want is this corner should be here, and then there, and then there. It might be like this or like that or like that. Doesn't matter. What matters for prescribed timing is this time the rotation of the crank. So the variables are changing. So still I have the same equations. Rather than alphas being known, this time betas are known or prescribed. What I'm going to do is I'm going to solve the same equations. I would need W and Z, and I can select unknown alphas arbitrarily. Each arbitrary set will give me a pair of Z and W, which corresponds to a candidate of A and A0 or B and B0. But once I find or select one of those sets, then actually I decide what the rotation is. So by using the same alphas, I can select another arbitrary set of betas, which correspond to the swing of this link. This time it's arbitrary, follower rotation. I can find W prime and Z prime to form the 4-bar. Okay. Is this clear? This is a bit tricky. Initially, we say rotation of this is specified, so we assume betas are known. We select a set of alphas, then actually we fix how this plane is moving, but for the follower, its rotation is arbitrary. You drive it from here, so it's prescribed. You select an arbitrary set of beta primes for your selected alphas previously to find these vectors. Okay? So that's another use of it. Now, we may use dyad equation alternative to Freudenstein's equation. That is, to correlate the crank rotations for 3-position synthesis. Remember, we started 3 positions by Freudenstein's equation, but we can use dyad equation for that as well. But let's have our 5 minutes break again before I start this. So we can use dyad equation for correlation of crank angles as well, which would be alternative to Freudenstein's equation. So the 2 students of Freudenstein, Erdmann and Sandor, developed an alternative method to their mentor's equation. But what is smart about Freudenstein's equation is it's real. And in terms of link length parameters, K1, K2, K3, it's linear. It's really very smart. So what Freudenstein did is, I would say, much smarter than this. But of course, this doesn't degrade, I would say, the dyad equation, because dyad equation can be used for many purposes, and this is one of the purposes if you would like to. So what you do is you define beta 2 as the rotation of crank from position 1 to 2, beta 3 from position 1 to 3, beta 2 prime as the rotation of the follower from position 1 to 2, and beta 3 prime as the rotation of the follower from position 1 to 3. So you have 2 dyad equations for the crank, or link number 2, and 2 dyad equations for link number 4. Now, here, as you might have seen, there's a trick. We have displacement of one representative point on the moving plane, which is the coupler, and displacement of another point on the moving plane, which is the coupler. We don't use the same point. What we do is actually delta 2, delta 3 are displacement of A from position 1 to 2, and delta 3 is from 1 to 3. That's displacement of point A. and this is point B. So what we have is, we have 1, 2, 3, 4 complex equations, or if you like, 8 scalar equations. We don't know W, we don't know Z, we don't know W prime, we don't know Z prime. We specify betas, the crank rotation, beta primes, the follower rotation. Alphas are free parameters. So what we have is, in Freudenstein's equation, we could select the initial positions of the cranks. Here, we have alphas as the free parameters. So still, we have 2 free parameters rather than these two, those two. So you can use Diet equation to correlate crank angles as well. But as you see, the equations are quite cumbersome compared to Freudenstein's equations, okay? Rather than solving 3 real equations for 3 real unknowns, you're going to solve equivalent to 8 real equations. And still you have 2 free parameters. You have to determine these complex variables as well. So I don't know if you would like to use this, but it can be done, okay? So that's another use of it. As I said, it's alternative to Freudenstein's equation, but it's cumbersome. What else can we do? Now, one important use is if we would like to determine the center point. Now, in graphical construction, what we were doing was kinematic inversion. In Diet formulation, we will just rearrange the equations. Not the original Diet equation, but we are going to define a new complex number, which is R. So what happens is, W is the vector on the crank, Z is the vector on the coupler, which we would like to determine the two so that we can construct the 4-bar. But we also define a vector R, which points directly from our representative point to the fixed pivot. So actually, simply R is negative W, negative Z. Remember, given P or selected P, we were finding A by solving Z and saying minus Z. And A0 was from A minus W or negative W. Well, that's okay, but to be more handy, we define a new vector R, which points from the representative point on the moving plane to the fixed pivot, okay? So that's just a new definition, which is handy. So what happens is we have this identity. W plus Z is negative R, or negative W, negative Z is R. So if you like, W plus Z plus R is 0. You still come to this unknown A0. And this time, when you solve W and Z, you can find R. But what we will do is, rather than using W, we will use Z and R. Okay? Negative Z defines what we call the circle point or the moving pivot, A, and R defines the center point or the fixed pivot. So we will just write the Diet equation including R in it as well. So what I am going to have is R plus W e to the I beta 2. So I move to my second position, Z e to the I alpha 2, and that's going to become delta 2, which is this. And for position number 3, I will have this. So as you see, I have introduced one more complex equation, one more complex unknown. So this is similar to if we omit R and use the original dyad equation as well. I will have the same free parameters. I will determine one more unknown, which is R, which directly specifies A0. But what I would like to do is this time I would like to select the location of A0 because maybe my design is dictating it. You should place your fixed pivots to here or within a region like this. Okay, so if I'm selecting the location of fixed pivots, this means R is known. What is unknown is still W and Z. The plane motion are known, so I know alphas. I know deltas, it's the displacement of the representative point. I'm going to solve for W and Z if you like, but actually what I need is only Z, or if you like only W if you select A0. So let's see how this time we solve. Delta 2, delta 3, alpha 2, alpha 3 are again given because you know the motion of the plane. WZ are not known. Beta 2, beta 3 are not known. These are the rotations of the crank. But you specify, as I said, R. That is, you select A0, but you can have a W and Z like this, or it could be like that. You don't know. You're trying to find it. And as I said, R determines the location of the center point, so you select it. You know it. Since we have 3 complex equations, 2 complex unknowns, and 2 scalar ones, that is actually you have 6 scalar equations, 2 unknown for W, 2 unknown for Z, 1 for beta 3, beta 2, 1 for beta 3. You have 6 unknowns. So once you select location of A0, you have a unique solution. Now, just remember the graphical construction. When we do the kinematic inversion, what happens? A0 is going to move to 3 points. Am I right? When you move the fixed plane. And those 3 points will define a circle in the inverted motion whose center is fixed, which is a unique A. And when you re-invert the motion to obtain the original motion, you will have 3 A's whose A0 is unique. So once you select the center of the circle, or in the inverted motion, when you select 3 points on the circle, its center is fixed. So this is what this equation is saying, okay? Once you select A0, which corresponds to determining R, you have a unique solution. But the trouble is, this time, the equations are linear in unknowns W and Z, but nonlinear in betas. So the solution is not that straightforward this time. To be able to solve these equations, we will rearrange the equations like this, okay? Now, those pink ones are unknowns, yellow ones are known. So I rearrange the first equation like this, where I have a negative r here on the right-hand side, which I'm going to call R1 arbitrarily, okay? So actually R1 points from A0 to P, okay? For the first equation. For the second equation, if I take R from here to there, I will have delta 2 minus R, which I will call R2. And since I select A0, this is also known. Okay? Similarly, in the third equation, delta 3 minus R, I will call it R3, and it's known as well. So my unknowns are WZ, beta 2, beta 3 that I have to solve. I have 3 complex equations, 2 complex unknowns plus 2 real unknowns. So they are equivalent to 3 complex unknowns, if you like, or 6 real equations, 6 real unknowns. However, this is a pain in the neck. The equations are linear in W and Z, but not in betas. So what shall I do? Given delta 2, delta 3, alpha 2, alpha 3, and I select what R is, that is the location of A0. I have, as I said, 3 complex equations and 2 complex and 2 scalar unknowns. So I have a unique solution once I select R. So how do I solve for it? This is what I have from the previous figure, and I'll just do a trick. I will use the determinant of so-called the augmented matrix. That is, I will choose beta 2 and beta 3 such that these 3 equations will become dependent, okay, not independent. So that's the trick. I will not tackle to all these 3 equations, which are nonlinear in 2 unknowns, but I will say, okay, I will choose beta 2 and beta 3 such that these 3 equations should be linearly dependent, not independent. And what's the condition of linear dependence? It is the determinant of augmented matrix being 0, okay? Whether the equations are linear in terms of unknowns or nonlinear, these equations are independent when this determinant is different than 0. Am I right? So that it has a unique solution. Else, if the determinant is 0, that means the rank is less. So at least one of the equations is dependent on others. So this is the trick I'm trying. I'm trying to make these 3 equations dependent by selecting beta 2 and beta 3, these values, which is the solution of this equation. Remember, that determinant is again complex, okay? R's are complex numbers, e to the i's are complex numbers. And 1 in general is a subset of a complex number. So that's a complex equation, okay? So I'm just forcing these 3 to be dependent, and I solve for the nonlinear variables. If I can do so, the rest would be simple. By using any 2 of those 3 equations, I can solve for W and Z because they're linear. So like Don Quixote attacking the windmills, I attack the harder variable by this trick. Is this clear to everybody? So that's a mathematical trick. It has nothing to do with mechanisms, but that's a nice trick. What I'm going to do is I'm going to expand this determinant. So what I'm going to have is something like this as my expansion, okay? This times determinant of this, which is this. Then I think I'm expanding it about this column. Negative this times determinant of this. And then this times determinant of this is equal to 0 is my first step in the expansion. And then I can determine these determinants very easily so that I will obtain a complex equation like this, which is, again, that's not a surprise, nonlinear in my unknowns. Okay, but I don't have W and Z in these equations. Once I determine betas, determining W and Z are simple. So this is the nonlinear equation I need to solve. And what I'm going to do is I will call this thing, which is known, a new complex number D1. Okay? This is something I'm trying to solve, and beta 2 is unknown. I will call all this a negative D2. So actually this would be plus D2 e to the I beta 2. Okay, that's a trick. And then I will call this, which is all known as D3 and e to the I beta 3. Now, what I have here is this. Let me copy the same equation to here. As you see, these two minuses will cancel. So I will have a D1 complex number, which I can represent by a vector. I have a D2 complex number, which I can represent it by a vector. And I have to rotate it by an unknown amount, beta 2. Am I right? E to the I beta 2 is a rotation, but I don't know how much I should rotate. And then another complex number, which I can call a known vector, and I have to rotate it by beta 3, and it should sum up to 0. So actually, I can have a graphical solution to this problem very easily, okay? Like this. These are three complex numbers. I drove the D1 based on the values I have. And then on tip of it, I drove D2, which is another complex number. Okay. And I also drove D3, which comes to the tail of D1. And I can do those because these are known complex numbers, okay? So what I do is I'll rotate D2 by an unknown amount. So this is the rotation of D2, where it's at the tip of D1. And this is D3. I'm going to rotate it on its tip like this. And it's going to yield 0 for actually two values, because these two circles intersect at 2 points. And this one is one of the solutions. You see, D1 plus D2 e to the I beta 2 plus D3 e to the I beta 3 is equal to 0. And the other one is this solution, D1 d2 e to the I beta 2 prime plus d3 e to the I beta 3 prime. So since this is a nonlinear equation, it's natural that we would have more than one solution, which we know from mechanisms very well. Okay, so that's the graphical solution, and actually you can obtain the angles exactly from a CAD software package. Of course, I just draw these for certain D1, D2, D3 values. You can draw it for any value, and you can obtain those two solution angles numerically very easily. Now, it's very interesting that one of those solution sets is identical to alpha 2 and alpha 3, which is not the solution you're looking for. So you will select the other solution. That is actually, the solution is unique, really unique. This set is not the one you're looking for. It's the other set. Okay? Then, by selecting whichever pair is not identical with alpha 2 and alpha 3, you can use these equations like this. I'm sorry, this is circle point specification. I'm sorry. Yeah, so this concludes what we would like to do, okay? You can return back, substitute the beta 2, beta 3 values you find from this into the previous set of equations, any two you like, either these two or those two or those two, because with this we made the three linearly dependent. You can solve for, actually what you're looking for is just Z. Or if you like, you can find W as well. It's from R, it points A, or Z, negative Z points from P to A. So let me just move up and try to explain what I mean. So one of W or Z is sufficient. Why? Because once you select R, you choose location of A0. If you solve W, W points point A from A0. You may solve it. Or you may solve just Z, negative Z points A from P. So whichever you like, you can solve one of W or Z is sufficient. But of course, if you would like to check, you can solve also the other one if it gives the same point, okay? But W points A1 or negative Z points A1. So it should be the same point if you would like to check. So if you solve one of those, that's sufficient. But for a selected A0, you will have a unique A. And this makes sense why in graphical design procedure, if you invert the motion, you will have three A0s in the inverted motion, which will have a unique center point, okay? So by changing location of your R, you can change the design. Okay, you can have different 4 bars. So if you have tight restrictions in center point, you can first select it and find the corresponding circle point if you like this, okay? So if you would like to select the location of the moving pivot, like in the graphical synthesis, This time, again, you can use this extended form of the dyad equation. This time, what you select is negative z, or z itself. You can call it z1. And then you can write the equation in position number 2, and z is going to rotate by an amount alpha 2, which is the rotation of the plane. You can call it a new complex number because once you select z, z times e to the I alpha 2 is something known. You could call it z2, and similarly for position 3, you could call it z3. So you will obtain another set of dyad equations. Now, this time, rather than using these as your free parameters, actually you use z. That is, you select where A1 is going to be, the first position of the moving pivot. So, still, you're given the displacement of the representative point on the moving plane and the rotation of the moving plane. You select z, which is the location of A1. You have, again, 3 complex equations, meaning 6 real equations. You have 2 complex unknowns, meaning 4 real unknowns, and 2 angles. So that's, again, is going to yield unique solution. And actually, the equations are very similar to center point specification, okay, if you would like to select the circle point. Just the variables are changed. But again, we have the trouble that the equations are beta nonlinear in beta 2 and beta 3, but we devised a smart method in center point specification, so we can follow exactly the same procedure, just the equations are slightly different, but the solution procedure is identical. Okay. Any questions up to here? It looks like we are going very quick, but when I assign the second homework assignment, and when you start using them, I think you would go over them and it would be clear. So shall we have another 5 minutes break? It's time. Well, another application is obtaining circle and corresponding center points using dyad equation. This time the problem is slightly different than the previous ones. That is, we do not do such selections, but again, we can utilize these 3 equations, or if you like, you can use the original form without R's and without this equation. They are equivalent, but that's an alternative formulation. Again, the motion of the moving plane are specified by the 2 displacement vectors and 2 angular rotations from the first position. Now, when we start from the representative point on moving plane, negative z yields the location of the circle point or the moving pivot, and r yields the location of the corresponding center point. And as I said, w would be redundant for that case, but if you like, you may solve for it to check your equations. What do we have as the unknowns? W, a complex number, Z, a complex number, R, a complex number, beta 2 and beta 3 are two real angles. That is 2, 4, 6, 7, 8 real unknowns. So like the original form of the dyad equation, you can choose beta 2 and beta 3 as your free parameters. That is, you can change them and obtain different solutions. How do we do that? We need R, which is the location of the center point relative to the first position of the moving plane, and the equation for R is like this. It's a ratio of two complex numbers, which are determinants of determinants of a 3 by 3 matrix. It's the ratio, and it can be calculated very easily on computers. So that gives the location of the center point once you select a pair of beta 2, beta 3 angles. And negative Z is the location of the circle point from the first position of the moving plane. And again, it's a ratio of two determinants. And what you can do is you can change beta 2 and beta 3 in a, if you like, double nested loop and obtain negative Z's, which are loci of candidate A's, and R's, the corresponding A0s. So, for example, if you say beta 2 is 30, beta 3 is 45 degrees, corresponding to this, you will obtain an A, which is the moving pivot or center point, which is a Z, and substitute the same values and obtain the corresponding A0. Then just change beta 2, I don't know, to 31 degrees, beta 3 still you may keep it 45, or you may keep this 30, you may keep this 40, you may make this 46, obtain another A, if you like, prime, and corresponding A0 prime, okay? So actually you have, if crank rotations are not specified, you have still two free parameters, very, very similar to the original form of the dyad equation. In that case, you were determining negative Z, negative W, or negative Z, negative W was showing A0. Here, it's just R. So it's just another form of the same type of equations. You will obtain another set, okay? So you will have a candidate A's and corresponding A0s, or B0s and B's. So that's the alternative formulation. Another interesting problem is, okay, what we were doing was we were looking for 3 points with its center. What happens if we would like the 3 points to be on a straight line rather than on a circle? Actually, mathematically speaking, straight line has its center at infinity. We can utilize this, or we can try to derive another set of dyad equations. Actually, this time we will derive another set of dyad equations. This is called actually straight line guidance. That is, one of the points you want it to be on a slider whose center of curvature, or B0, is at infinity. So what we will do is this actually. This time we want such a point that its all positions are on a straight line that makes gamma angle with the real axis. Okay, so A1 is here, A2 is somewhere on this line, A3, A4, whatever. So I'll call this general point AJ. All positions of this point A should be on this straight line, okay? So what I do is, whatever displacement I have, which is a scalar, I will call it Sj because it's always on the same line, which makes an angle gamma with the real axis. So I have a displacement Sj e to the I gamma j, which is this, plus let me make it this way. Let me first write this side. Z is an unknown vector from a point A whose all positions are on a straight line. So I'm looking for Z. So this is my Z, and delta J is this vector. It's displacement of this representative point from position 1 to position J. So this is the right-hand side, okay, where Z is an unknown vector. So I'm looking for this unknown point A whose all positions are on a straight line. In the displaced position, what I have is this unknown point A is going to move a scalar amount Sj along this slider whose orientation is gamma j, which may be specified or we may be free to select it, plus this unknown z vector is going to rotate while it's moving, z e to the I alpha j. So I'm still at this point. So this is how I derive the dyad equation for straight line guidance, similar to previous derivation. And of course, I can rearrange it similar to previous dyad equation. I have z on both sides, so I can take this to that side. So I have z e to the I alpha j, where alpha j is the rotation of the plane in jth position, minus 1 because of this, plus this is equal to my delta j. And for 3 positions, it's j equals 2 and 3. So I will have 2 of those equations, z e to the I alpha 2 minus 1 plus S2 e to the I gamma is equal to delta 2, and z e to the I alpha 3 minus 1 plus S3 e to the I gamma is equal to delta 3. Okay. Well, the 2 or the 3 positions of the plane are defined by delta 2, delta 3, and alpha 2, alpha 3. We have to find z, which is a complex number, where negative z points my A, whose 3 positions lie on a straight line. S2 and S3 are 2 scalars, so that it's on the same straight line, but they're unknown. Gamma is the orientation of the slider axis relative to the real axis. So I have 2, 3, 4, 5 unknowns, 2 complex equations, so 4 scalar equations. I have only 1 free parameter. And if you check these equations, this is one of the unknowns. 2 of those, S2, S3, are the other 2, and gamma is the third. Now, the good thing is It's only nonlinear in gamma, and I have a free parameter. So I can keep the orientation of the slider axis as my free parameter if I like. But if I do this, actually, I'll put the equations in a more manageable form. I will call lambda the ratio of S3 to S2, which is a real number because S3 and S2 are real numbers. These are displacements. And actually, you can set lambda larger than 1. In that case, S3 would be larger than S2. You could make lambda between 0 and 1. In that case, S3 is smaller than S2. Or you can make lambda even negative. In that case, S3 and S2 will have opposite sides, okay? If one is on the right, the other one is on the left, but you can't determine which is which, okay? Because we take the ratio. However, that's not important. You can make all of those. Then you can define a new complex variable. This is not conjugate. I just put the bar to show that it's a complex number as S2, the real number, e to the I gamma. Okay, so that's a complex number. Then you can define S3 e to the I gamma as lambda S2, where S2 was S2 bar, where S2 was this S2 bar was S2 e to the I gamma, which is a complex number. So these are complex numbers. Then the Dirac equations will take this form. Z e to the I alpha 2 minus 1 plus, for this S2 e to the I gamma, I insert a complex number, which is S2 is equal to delta 2. And Z e to the I alpha 3 minus 1 plus lambda S2 is actually S3 e to the I gamma. Since they're on the same straight line, these two are the same complex number multiplied by a scalar is equal to delta 3. And this form of complex equations are more handy. What we have is actually two complex equations in two complex unknowns, I should say, it's missing, which are Z and S2, and we have one real parameter, lambda. So I can use lambda as my free parameter to solve these two complex equations in two complex unknowns very easily, like this. So these were the equations I have obtained. I obtained negative z, not z, because negative z actually points the point I'm looking for, whose three positions are on a straight line from P, and it's just this determinant, okay? And you can also solve for S2, which is a complex number, which is a ratio of this determinant. And what you can do is either you can change lambda in between any practical values you like, or theoretically, actually, it can vary from minus infinity to plus infinity. So you're going to obtain the location of your point, and also S2 shows a complex number, which is the displacement of point A from position 1 to position 2, which also contains the angle gamma. So actually, if you just change lambda from negative infinity to infinity, given three positions of a plane, you obtain locus of points on that plane whose three positions lie on a straight line where you can attach a slider. Now, in some designs, you may not be free to select the direction of the slider axis. It might be fixed or it might be in a limited range. If it's fixed, that is, for example, you want a horizontal slider where gamma is 0, or I don't know, you want a slider that makes, I don't know, 30 degrees or 45 degrees or 90 degrees angle, then actually you can do a solution directly. Oops, I'm sorry, I just did something wrong. You can do a solution directly, which is this. Your z, or if you like negative z with a minus sign, would be this. And actually, that is a circle. When you change gamma, if you have a fixed gamma, then you find a unique point whose 3 positions lie on a straight line. So actually, you have seen the final slide. This ends the 3 positions of a moving plane. We will start with 4 positions after the midterm exam.